Hello and welcome to Aerospace and Mechanical Lab 2. Today we are going to talk about how to use ANSYS to do a computational fluid dynamics analysis. Of course, the first thing you want to do is to open Workbench. I'm going to search for Workbench. This is the software we have also used for the previous lab. If you search for Workbench, you see that ANSYS gives you two options. One is a reaction workbench, one is a regular workbench. This is the software of interest for us, regular workbench. I'm going to open it. Usually it takes a little bit of time for us to open. If you are on a lab computer, you want to cancel all of these because we don't have admin access, so we cannot allow any access, basically. And our goal here would be to analyze the fluid flow around a 20 centimeter by 20 centimeter square within a 1 meter by 1 meter domain. Okay, so again, same environment as before. The difference would be here that we want to use a different module, and the module that we are interested in is the fluid flow module. So you can see there are a lot of fluid flow modules here. One is with CFX software, the other is with Polyflow, and we have two Fluent software. These two are the ones that we are interested in. One gives you an option to generate your mesh with Fluent. The other gives you the option to generate the mesh with ANSYS, which is the what we want to do. Okay. You drag and drop, you have your geometry, mesh, setup, solution, and results. Again, you want to right click on the geometry to open design modeler. If you do want to use a space claim or discovery, that is also all right, but this design modeler is the thing that we want to discuss. Okay, again, cancel, we want to use. Usually it takes a little bit of time for this to open up, so please bear with us. Yes. Okay, so we are here in this domain. We have already seen this. This is going to be a two-dimensional domain. Okay, so I'm going to click on the z-axis so I can only see the x, y plane, right? And we want to sketch a square, right? How do we do that? We go from modeling to sketching. And then we can either sketch a rectangle or we can use the lines that we have. One thing that you want to notice is that the scale here goes from 0 to 30 meters. What does this mean? It means that this distance here is 30 meters. And this is not the distance that we want to focus on. So I'm going to zoom in a little bit. So I think this should be fine. So this distance here is 4 meters. Let's actually do 2 meters. This distance is 2 meters. So we are close to our scales of interest. I'm going to choose the rectangle. I'm going to start from the center of the coordinate system. Then I'm going to create a square. Doesn't have to be the exact dimensions. Just needs to be, I guess this is closer to 1 meter. Let me zoom in a little more. And here we can add dimensions. Make sure that our dimensions are correct dimensions. 0.5 meter by 0.5 meter. Need to change this to 1 meter by 1 meter. I'm going to zoom out a little bit. So this is our enclosure. The thing that we want to do here is we want to make sure that we have a square in the middle. It doesn't have to be exactly in the middle of your geometry, but we want it in the middle. So it doesn't have to be exactly in the middle. And we're going to learn how to actually put it exactly in the middle of our geometry. This is supposed to be 20 centimeters by 20 centimeters. So the first thing I'm going to do before moving it to the exact location will be going to dimensions and do the general dimension again. And you want to click on this line and move your mouse cursor out. This is how you can change the dimension. So V3 is this dimension, is 24 centimeters. We want to change it to 20. And this one is 31 centimeters. We want to change it to 20 again. So how should we move this to the middle? Of course, we can use the modify, but we can also use the dimensions. Like the vertical distance is the thing that we want to use. We want to change the vertical distance between this edge and this edge. For this square to be in the middle, this has to be 40 centimeters away from this edge. So I'm going to change this V5 to 40. It just needs to move a little bit, and then the horizontal distance here between these two has to be also 40 centimeters. There we go. So this is our square is in the middle of the enclosure. Again, it doesn't really need to be in the middle, but yeah, it might actually be a better idea for us to move this to the front, to the upstream, so we can analyze what is happening in the back, so we are not limited by the size of our control volume. I want to keep it in the middle for now. I'm going to hit generate and then go back to modeling, and here we essentially can do a couple of different things. In your lab memo, we have asked you to actually create these squares from here, but right now I did create a sketch. You can follow this, you don't have to follow the lab memo. The lab memo is not the complete instruction, so it might be better for you guys to follow this recording rather than the lab memo. Well, how can we create our geometry? Right now this is just a couple of different lines. This is just a sketch. This is not a surface. What I'm going to do is I'm going to go to this concepts on top here, go to surface from sketches, and then choose these lines. Sorry, let me. I'm working on a Mac, so my control button doesn't work. That's why I need to hold the left mouse button to do this analysis, to do these selections. Okay, we're there. And then hit generate. So this created the geometry desired for us. In the lab memo though, I've asked you to create two separate squares and then use the Boolean operation right here. This is the Boolean operation to subtract the smaller one from the bigger one. But right now, since we are already here, we do not need to use the Boolean operation, but you do need to do an explanation about it in your final wrap, just a little bit of why would you want to use Boolean operation. But the idea is pretty simple. If you create two different squares, if you add them on top of each other, you will have two sets of squares that you need to subtract one from the other one. But our geometry is ready for now, so I'm going to close this and go to meshing. Double click on the mesh. it will take a little bit of time again. So we just have to wait a little bit for our geometry to be imported in here. It's a two-dimensional geometry, so we want to make sure we actually have it in 2 dimensions. This is your surface body. Everything is clear here. I'm gonna click on the mesh right here. It says physics preference CFD, which is fine. This is what we want. Solver preference fluent. And then we have a default element size. Right now it is set to 7 times 10 to the -002. We want to change this to, we have a 1 meter by 1 meter, and this is 20 centimeters by 20 centimeters. And I want to change my biggest element to 1 centimeter, so 0.001. Or we can go a bit higher. Let's go to 5 centimeters. This is my biggest element size. So what I can do is I can hit generate, and it will generate a mesh for me with this as the biggest element size. But I want to have a coarser mesh around where we don't have a lot of action, so these parts, and a finer mesh around this edge. So what I'm going to do is I'm going to right click on the mesh, insert, first of all insert a method to my mesh, click, and then select apply. I'm going to change this quad. We can change it to triangle, multi-zone, or automatic. We're going to use quad because that is essentially a structured mesh with that do look like a square. This is a fairly good simple geometry. We should not have any issues using the quad meshing system. And then I'm going to add a sizing. So for the sizing, I'm going to come here. I'm going to change my selection from the body to edge. And these are the edges. Again, we want to select a couple. So I'm going to hold the mouse button. These are the edges that I want to control the sizes of. I selected those. I'm going to hit apply here. And then I'm going to change the default element size in these meshes to 0.00, 0.00. So 0.005, so 5 millimeters. I think I did set the wrong number here. This 5, we want this to be 5 centimeters, so 0.05. So on the meshes and close to my meshes, I'm going to have a smaller cell size, and further from my mesh, I'm going to have a larger cell size. We are ready to hit generate here and go from there. Okay, there we go. So this is not the best mesh we can use, and this is happening because we are using a structured mesh, and we don't have a good growth ratio here, and it's a small geometry. All of these we can do. So there are a couple of things we can do to. This is a problematic mesh. We don't want to use this in our analysis. There are a couple of things we can do. We can change this quad dominant method to triangular method. That will help this alleviate this problem a little. But we can also come here to the growth rate. This is defaulted to 1.2. If you use a value of larger than 1, of course, your cells are going to be becoming bigger and bigger by a factor of 20%. Or 10%, whatever that value is. But if you use a number that is below 1, your cell size is going to become essentially smaller and smaller and smaller. So this is not going to be a growth rate, it's going to be a shrinking rate if it's smaller than 1. So the value has to always be larger than 1. It was 1.2. I'm going to change it to 1.1 and see the effect of it. Again, mesh is a little more structured, but not as much as I want it to be. What I'm going to do is I'm going to change this growth rate now, and I don't expect to get the best mesh, but we are seeing a good enough mesh around our geometry. And if I didn't get the mesh I wanted, I'm going to change this to triangular mesh. There we go. So the mesh is better, but we do see a lot of inconsistencies still. I suspect if you make the growth rate smaller, closer to 1 essentially, that should fix the problem even more, but we want to make things easy, so we go to triangles instead of quads, and we're going to see that we're going to get a much better mesh with the triangles. See? We see some problematic areas, but these are not very dominant and important. So we have our mesh. Our mesh is ready to go. The next part would be we need to name our boundaries, all of these edges. So how do we do that? We want to make sure our selection is on the edge again, and select each edge. This one, I'm going to name this inlet because this is our inlet. This one, I'm going to name this as outlets. For the top and the bottom, this is supposed to be flow inside the pipe, but we are not really interested in what is happening around these walls, and they are not close enough to our square to have meaningful interactions with the square. So we can set these to false and we can name them as well, or we can just use inlets for this as well to make our simulation easier. So I'm just going to use inlet again, create name selection. I'm going to call this inlet top, and this one I'm going to call inlet bottom. And okay, and all of these, again, I'm going to select all of these and name them all walls. So these are going to be walls. Okay, so we have our name selection, our boundary names ready. This is the inlet, the outlets, inlet top, inlet bottom, and the wall. And our mesh is also ready. I'm gonna close this. You see, this is not a check mark, so I need to right click and update to make sure we do get a check mark. So right click, update. This is how the software works for Fluent. But if you use ANSYS meshing, you need to update your mesh after you have generated the mesh, so it can import the mesh to Fluent. Maybe this is a time-consuming process a little bit. This is done now. Maybe you do see the check mark, and we can open our setup. We do not need to change any of these except for this number. If you increase this number, if you are at home using the free version of ANSYS, you can go up to only 4 processors, but if you are not at home, if you're using a lab computer, you can go as high as the number of CPUs we have in the system. I'm going to stick to 4 because we don't need to use that many CPUs for this specific simulation. It is not that time consuming. Okay. Okay, so our mesh is generated now. We do need to check the quality of the mesh. So you can see here the option. You see this is our in general tab. You see a lot of options, but the options on the top are essentially the extension of what we have on the left. These are, as you can see, we have general, models, materials. Same thing here, solver, models, materials, zones. All of these things are exactly the same options. It's just this one on the top we have a more extensive set of selections, but we are going to use the a menu on the left for our analysis, and whenever you click on something here, it will open up a new menu just beside it. Double click on general, we have all of the options in our general menu. We have mesh, solver, and we can also activate the gravitational field. So we can scale our mesh, we can check our mesh, report the quality of it, display, and check the units. Let's check the mesh. Check mesh is done. You can see it. We do get a lot of information in our domain in our console here. It tells where the x coordinate begins, where does it end at 1 meters, and gives us a lot of ideas about the total volume, the face areas, and whatnot. We can report the quality. So you see the minimum orthogonal quality is 0.6. The skewness essentially is 0.6, and the aspect ratio is 3.99. This is a somewhat large aspect ratio, but it will do the job fine for us. So these two numbers are the numbers you want to report in your lab reports. You want to make sure you actually record these numbers. As you can see, these three walls, these three parts are the inlets, this one is the outlet, and this is the valve. Next step here would be to go to the models. Right now, these are different physics you can activate. The only thing that we really need to care for is the viscous model. The viscous model, we have a lot of different viscous models. We can have an inviscid model, a laminar model, or any of the turbulent models. We can solve a laminar problem using any of these turbulent models, but we do not need to do this. So one thing you want to check is the value of Reynolds number for your specific problem. And then if the value of Reynolds number is smaller than 10 to the power 5, then you can come here and select the laminar. What is the benefit of using laminar? It is just faster. That is the only reason you would want to use laminar. So, but that Reynolds number calculation is very, very, very important. Okay, and the material here, you want to make sure your material is selected to be air. It is already here. We do not need to change anything here. All of the other options, this will help you to create a specific zone in your cells with a specific temperature, specific different velocity, or whatever, right? And the boundary conditions is going to set the values at the boundaries. We do need to set the values of velocity here specifically. Okay, so on the boundary conditions, it will give us all of the boundaries. We have an inlet, we have an inlet at the bottom, inlet at the top, we have an interior surface, we have an outlet, we have wall. You click on the inlet, it gives you an option here about the type of the inlet, a lot of different options, but you do not need to change this. A velocity inlet is fine. You want to edit this, and then you want to change these. It says velocity specification method, magnitude, normal to the boundary. So this is fine for this inlet, but it is not going to be fine for these two inlets, because our inlet velocity has to always be in the x direction. So on this top, you need to make sure that the inlet is also, the velocity field is moving in this direction on the edge itself. I'm going to change this from magnitude to the normal to the boundary to magnitude and direction. Our magnitude, we have two different magnitudes. One is 0.1 meters per second, and the other one is 0.01 meters per second. I'm going to start with 0.01 meters per second for velocity magnitude. We are asked about supersonic initial gauge pressure. There is no need to change that for this specific scenario. And then the x component of velocity direction is 1, y component 0. So at this inlet, we are saying that we are always moving in this direction. We're going to do the same for these two inlets. So I'm going to hit apply and then close. Go to the inlet at the bottom, velocity inlet, edit, same thing. Has to be 0.01, and then x component 1, y component 0. velocity inlet, edit. Again, 0.0, 1, 1, and 0. Apply, close. The outlets, again, a couple of different options. We need to keep it as pressure outlets, and there's nothing we need to edit here. We do have a couple of options, but there's nothing we need to change. For the balls, we only need to make sure that it is set to a ball. And if you name this a ball, it is already set to a ball. It is not a moving ball, and we have no slip condition already set. So we are good to go for the boundary conditions. All of these other options are the more complicated options that are not going to be included in this lab. But if you're interested, you should definitely go back and learn more about these things. Then we have the setup figured out. I'm going to close this menu. The next part is solutions. In the method section, it will ask you about the type of mathematical method you want to use to solve your governing equations. I do not expect you to know any of these, and I do not expect you to change any of these, but the general idea is if your method is of a higher order, see first order, second order, and third order, you will get a more accurate result. For this specific scenario, a second order method, which is already set by default, is good enough. Okay, and the next part is controls. Again, these are going to change the time it takes for us to converge to a solution. If the value is closer to 1, it is going to be faster. The value is closer to 0 is going to be slower. Why would we want to have a slower convergence? Because of stability concerns. Are we concerned about the stability of this specific scenario, the specific problem? Not really. So we don't really care about these. The report definitions, these are the things you can actually define. If you want to, you can measure the forces that are being exerted on this square. You can do whatever you want to do. Again, not a part of this lab. But the thing that is a part of this lab is the monitors. So if you open the monitors, it will give you an option to change the value for that residuals, that error. It is set to 0.001, which is 10 to the negative 3. But we want to change this to 0.004, 10 to the negative 4 for all of these, because we want to have a more accurate result. The rest of these, again, not a part of our analysis. If you have watched the lecture, you already know that we usually start with an initial guess and go from there. And we need to initialize our problem for that initial guess. We have two different types of initialization in ANSYS. One is hybrid initialization. The other one is a standard. We want to go with hybrid because essentially this is a smart artificial intelligence informed type of initialization. It usually works better for your specific problems. Okay, the only other thing that is left for us is to run the calculations. To run the calculations, you have a pseudo time setting. That is not something that we want to concern ourselves with. This is essentially for a transient problem where changing of time is important. That is not important to us. We are only looking at one snapshot of a time, a steady state scenario. And the only reason we need to iterate it essentially is not because we are marching in time, it's because we are guessing the solution and we need to come below a specific error. I'm going to set this to 500 and hope that we can reach the desired value of error or residual before the number of 500 is reached. But if it is not reached, we are just going to keep running another 500 iterations. So the only thing that is left here is to click calculate. When I click calculate, we're going to see the residuals show up on here. Usually start from a very high value of residual error, and then it will go down until it reaches the desired error value. Okay, so it actually converts pretty quickly. You can see this, the continuity, the conservation of mass was the last thing that converts, and the desired value after 48 iterations we have reached 1 to the negative 4, 10 to the negative 4, which was our desired values. Okay. So we have our solution, we have a solution that we wanted to. We can go back to, we can close this and go back to results and look at the results from here, or we can use Fluent software itself to look at the results. Right here, there are a couple of results that we want to look at, and all of them are graphics. Of course, you want to make sure that your mesh is included in your report. You want to double click on the mesh. It will give you a lot of different options. Do you want to look at the nodes, edges, faces, whatever? And then you want to make sure that all of these are selected. Select display. This is your mesh. This is what you need to put in your lab reports. How do we export these values? We can save this as a scene. We can take a screenshot using our keyboard, or we can come here and export our solution data and draw the graph in a different software. Doesn't really matter what you want to do. You can just, but you cannot, or we can save picture right here. You cannot use your phone to take pictures of the screen. So it's pretty simple. Right click, save picture, and it gives you a lot of options. Formatting, the color, do you want it to be a monochrome or color? We want color, and then you save it. It will ask you where to save it, and then you will be done. And this is your for mesh. And whenever you want to come back to this, this is saved as mesh 1. For the contours, we want a contour of pressure on all of these surfaces. We do not really need to change any of these options. I'm gonna hit play. You can see it gives me the pressure all over my geometry. We can actually have the contour lines as well. Okay, there we go. We have the highest pressure here, which was expected, lowest pressure here, which tells us that there might be some flow separation, and this will be your contour of pressure. Okay, we can actually have this as field. We can have boundary values or not have the boundary values. Let me actually have this as fields, and then go from here. We can remove all of the boundaries and have only the interior surface. You can do a lot of different things with these contours, and then you can save this, present it to your graph. The next thing that we want to see is the vectors of velocity. Again, the option is right here. Double click, velocity vector, and we want to color it by the magnitude on all of the surfaces. Display. You can see all of the contours right here, the vectors right here. This is expected. We don't want to see a 3D arrow. We want to see just a regular arrow. It's easier to visualize and understand. Right here we can zoom in and see, you can see all of the flow separation regions, all of the vortices of interest. There are a lot of options we can actually change. We can change the size of these, the scale of these vectors. It is already set at 1. You can change it if you want to. If you want to make these bigger or smaller, doesn't really matter. You can change the contour values. And the value of velocity is right here. Okay, done. The last thing we want to do is to draw the streamlines and the path lines. Okay. Double click, There's nothing you really need to change here. You just need to select all of them, save display. The streamlines usually take a little bit of time because there's a lot of time that need to be processed. It will give you a good visualization of how the flow actually looks like. You want to save all of these, and you want to go back and change your velocity, and you will be done with the lab. Please let us know if you have any questions, and have a good rest of the semester. Good luck with all of your exams.